In 1991, in a paper in the journal Science, 3 astronomers, Juan Uson, Boughn, and Jeffrey Kuhn, published a careful measurement of a single galaxy at the center of a cluster of galaxies in the constellation Serpens. They had spent years carefully imaging the faint outer light of this galaxy, light so faint that it was less bright than the night sky itself, and had pieced it together from long, dark exposures into a single, coherent. The picture showed something almost no astronomer of the time had been prepared to see. The galaxy was vast. It extended outward in a smooth halo of starlight to at least 6 million light-years across. 6 million. Our entire Milky Way is, by comparison, perhaps 100,000 light-years from end to end. The galaxy at the center of the Abell 2029 cluster, the galaxy known as IC 1101, was at least 60 times wider than ours by their measurement and held within its diffuse halo something on the order of 100 trillion stars. Our Milky Way contains, by the best modern counts, perhaps 2 to 400 billion. IC 1101 is, by stellar count alone, somewhere between 250 and 500 times more populated. This is a long, calm telling, in the dark, about the largest, oldest, strangest galaxy that human astronomy has so far been able to measure. We will walk slowly through how astronomers measure the size of a galaxy, the supergiant elliptical class, the deep history of IC 1101 itself, the cluster of 2,000 galaxies it sits at the heart of, the galaxy cannibalism that built it, the supermassive black hole at its core that may be one of the most massive in the known universe, the slow death of its red giant population, and what this single object teaches us about the largest scales of cosmic structure. The lights are low, the day is finished. Let the cathedral of stars continue to assemble itself on its own slow clock while you sleep. If you find this kind of long, calm telling useful, tap subscribe and tell me down in the comments where you are listening from tonight, just the city or the country or the room. I read all of them in the morning with my coffee. Part 1. The faint smudge in Serpens. Here is the headline object. The galaxy at the center of this evening's story is called IC 1101. The name itself is unromantic. It is an entry in a catalogue. The letters I and C stand for Index Catalogue, the catalogue of nebulae and star clusters published by the Danish-Irish astronomer John Lewis Emil Dreyer in 1895 as a supplement to his earlier New General Catalogue. The 4-digit number is simply the position of the entry within that catalogue. There are several thousand objects in the Index Catalogue. IC 1101 is one of them. By name alone, it does not announce itself. Here is what IC 1101 actually is. It is the brightest galaxy at the center of a galaxy cluster called Abell 2029 in the constellation Serpens, just over 1 billion light-years from Earth. It is, by every modern measurement, one of the largest individual galaxies that has ever been catalogued. By the most generous halo measurements, IC 1101 extends out to about 6 million light-years from end to end. By more conservative measurements that count only the densest stellar regions, it extends out to roughly 400,000 light-years across. Either way, the galaxy is enormous. Either way, IC 1101 is far larger than our own Milky Way galaxy, by factors that range from 4-fold to 60-fold, depending on which measurement you accept. Here is the discovery story for IC 1101. The galaxy was first spotted by the German-born British astronomer William Herschel in 1790, sweeping his 18-inch reflecting telescope across the sky from his observatory at Slough, west of London. Herschel was, in that era, the most prolific cataloguer of nebulae and faint sky objects who had ever lived. Working with his sister, Caroline Herschel, he had compiled a catalogue of 2,500 nebulae, faint smudges of light that, in his telescopes, looked like patches of luminous fog against the black background of the night sky. He could not, with the instruments of his time, resolve those smudges into stars. He could only note their position, their approximate brightness, their approximate shape, and move on. IC 1101 entered his catalogue under a different designation, listed as a small, faint, nebulous object. It was, in 1790, just one of thousands of faint smudges that William Herschel logged in his careful nightly sweeps of the sky. He could not have known what it was. He could not have known how far away it was. He could not have known that it was, in fact, one of the largest stellar systems in the known universe. Here is what we now know about that smudge. IC 1101 is 1 billion light-years from Earth. The light arriving in our telescopes tonight left the galaxy when single-celled life was the most complex form of biology on Earth, and the first multicellular organisms had not yet appeared. The galaxy has been there, on its slow internal clock, for the entire history of complex life on our planet, plus another billion years on top of that. By the time the photons we are now observing began their journey across the cosmos, the Cambrian explosion was still 500 million years away. Continents were drifting, the Earth was a different colour, and IC 1101 was already an old galaxy, already hundreds of billions of stars in its diffuse halo, already the dominant central object of its cluster, already growing in slow, patient, gravitational fashion through the steady accretion of smaller galaxies that drifted close enough to be captured. Here is the controlling image I want you to hold. IC 1101 is the cathedral of stars. A vast, slow cathedral built over billions of years through the gradual gathering of smaller stellar systems hung in space at the center of a cluster of 2,000 galaxies, glowing faintly red with the light of stars that have themselves grown old. We will return to this image throughout the evening. The cathedral. Here is the deeper observation about catalogues like Herschel's. The kind of cataloguing work that William Herschel was doing in 1790 was the slow, patient kind of work that science depends on, but which rarely makes the popular histories. Herschel was, on most clear nights, simply pointing his telescope at successive patches of the sky and writing down what he saw. He could not have known which of his entries would, 2 centuries later, turn out to be remarkable. He could not have known that one specific entry among thousands would turn out to be one of the largest stellar systems in the visible universe. He simply catalogued. He moved on. He came back the next clear night and catalogued some more. The patient accumulation of small observations over years and decades gradually produced the catalogue that subsequent astronomers would mine for their own discoveries. The cathedral, in this sense, was hidden inside the catalogue for nearly 2 centuries before it was recognized for what it actually was. Here is one final observation about IC 1101's role in the broader universe. The galaxy sits, as we will see, at the center of one of the richest galaxy clusters within 1 billion light-years. It is one of the brightest galaxies in our cosmic neighborhood. In absolute terms, it is one of the largest, by physical extent, that has been carefully measured. And it is, by historical accident of cataloguing, one of the few cluster central galaxies that is referenced almost exclusively by its catalogue number. Most popular accounts that mention IC 1101 do so because of its size. The galaxy has acquired, in the past decade or so, a kind of celebrity in popular astronomy as the largest known galaxy. The celebrity is partially deserved and partially a bit overstated, since the precise definition of size depends, as we have walked through, on which boundary you choose, but the celebrity, accurate or not, has had the effect of bringing wider attention to the existence of such objects and to the question of how they form. That is, in the long run, useful for the science. The cathedral has, through its accidental fame, recruited new generations of observers to study cluster central galaxies more carefully. Part 2. Reading the size of a galaxy. Here is the prerequisite question. How do astronomers actually measure the size of a galaxy? The question seems straightforward, but is in fact full of subtle problems. A galaxy does not have a sharp edge. A galaxy is, in physical terms, a gravitationally bound collection of stars, gas, dust, and dark matter, embedded in an extended halo that fades smoothly into the surrounding intergalactic medium. There is no clear boundary. There is instead a brightness profile that drops steeply at first near the densely populated central regions and then more gradually far out into the faint, diffuse halo. Where you decide to draw the boundary depends on how faint a measurement your instruments can make. Here is the practical method. The standard way to measure the size of a galaxy is to choose a brightness contour, a line of equal surface brightness on the sky, and to take the size as the diameter enclosed by that contour. Different astronomers use different contours depending on their observational sensitivity. A relatively bright contour, what is called the 25th magnitude per square, arcsecond contour, traces only the densely populated inner regions where stars are easy to detect. A much fainter contour, like the 28th magnitude per square arcsecond contour, traces out the faint diffuse halo of older stars that extends far beyond the dense centre. The size you report depends fundamentally on which contour you have used. Here is what this means in practice for IC 1101. If you take the bright 25th magnitude contour, the standard contour used to compare galaxies in many surveys, IC 1101 has a diameter of roughly 400,000 light-years. That is already 4 times the diameter of the Milky Way. By that standard, IC 1101 is a very large galaxy, but not unprecedented in size. There are several other supergiant ellipticals, including the famous Sombrero hat-shaped galaxy and the cluster central galaxy in the Coma cluster, that are within a factor of 2 of this measurement. Here is the more dramatic measurement. If, however, you take the much fainter contour, the contour that traces the diffuse halo of old stars at the very edge of the galaxy, IC 1101 extends out to between 3 and 6 million light-years from end to end, depending on which study you cite. That measurement was first carefully made by Juan Uson, Stephen Boughn, and Jeffrey Kuhn in their 1991 science paper, and it has been substantially refined by subsequent work. The most generous measurements, working with very deep imaging from large modern telescopes, place the outermost detectable stellar light at almost 6 million light-years across. That is 60 times the size of the Milky Way. That is a stellar system that, if you were standing on the surface of a planet at its centre, would extend across roughly half the distance to the next galaxy cluster. Here is the technical point that matters for what comes next. The reason these 2 measurements differ so dramatically is that IC 1101 has a diffuse halo of very old stars that fades extremely gradually into the surrounding cluster. The dense inner regions are about 400,000 light-years across. The faint, diffuse outer halo extends another 5.5 million light-years beyond that. The dense centre holds most of the stars by number. The diffuse halo, while much larger in volume, holds far fewer stars per unit volume. Both regions are, by the strict definition of a galaxy, part of IC 1101. The galaxy bleeds outward, gradually, into its surrounding cluster. The boundary is not sharp because the underlying physics does not produce a sharp boundary. Here is the comparison with our own galaxy. Our Milky Way, when measured by the bright 25th magnitude contour, is about 100,000 light-years from end to end. When measured by the faint outer halo of old stars and globular clusters, the Milky Way's halo extends out to perhaps 400,000 light-years from the galactic center. So even our own galaxy has a brightness-dependent boundary. But the contrast is far more dramatic in IC 1101 because its halo is so much larger and so much more diffuse. IC 1101 is not just a large galaxy. It is a galaxy whose outer regions are unusually extended for its mass. It is the kind of stellar system that you might call, with some metaphorical license, a galactic cathedral. The dense center is the nave. The diffuse halo is the surrounding architecture, the buttresses and spires that extend gently out into the surrounding sky. Here is the de Vaucouleurs context that is worth holding in mind. The French-American astronomer Gérard de Vaucouleurs, working at the University of Texas at Austin in the mid-20th century, established that the surface brightness profiles of elliptical galaxies follow a particular mathematical curve, the so-called r⁴ law. The curve is steep near the center and flattens further out, fading smoothly into the surrounding sky. De Vaucouleurs' work in 1948 and 1953 was the first systematic attempt to characterize elliptical galaxies as a coherent class. His r⁴ law has been the foundation of elliptical galaxy studies ever since. IC 1101, like other supergiant ellipticals, follows the de Vaucouleurs profile in its inner regions, but adds an additional, very extended outer component beyond the standard fit. That extra component is what gives CD galaxies their characteristic name, and what makes IC 1101's effective radius so much larger than what a strict de Vaucouleurs fit would predict. Here is one further observational note. The faint outer halo of IC 1101 has been studied with progressively deeper observations over the past 3 decades. Early work in the 90s by Uson and others established the basic extent of the halo. Subsequent work by John Tonry, Mark Postman, Patrick Coté and others using Hubble Space Telescope imaging and ground-based deep surveys has refined the surface brightness profile in the outer regions. The most recent work, using the dark current limited deep imaging from the Hyper Suprime Cam on the Subaru telescope and from the Dark Energy Survey, has extended our knowledge of the very faintest outer halo light to even greater radii. The picture, after 30 years of progressively deeper observations, is of a galaxy whose halo is genuinely vast, not an artifact of any single instrument's particular sensitivity, but a real physical extent that many independent observations have confirmed. Part 3. The supergiant elliptical class. Here is the broader category. IC 1101 belongs to a class of galaxies called supergiant ellipticals, or, in some classification schemes, type CD galaxies. The CD designation comes from the work of the American astronomer Sidney van den Berg in the 1960s and refers specifically to the brightest galaxy at the center of a rich galaxy cluster surrounded by a very extended, diffuse halo. The lowercase c denotes that the galaxy is exceptionally luminous, and the uppercase d denotes that it has a diffuse, extended halo around it. The CD galaxies are not the largest galaxies in the universe by every measure, but they are, on average, the brightest galaxies in their respective clusters. They are, in this respect, the bishops of their cosmic dioceses. Here is what we now understand about how CD galaxies form. They form at the centers of rich galaxy clusters, where the density of galaxies is high, and where mergers between galaxies happen relatively frequently. Over billions of years, the galaxy at the center of the cluster, sitting at the bottom of the cluster's gravitational well, gradually attracts and absorbs smaller galaxies that wander too close. Each merger adds stars, gas, and dark matter to the central galaxy. Each merger also adds a small amount of orbital angular momentum, which is mostly cancelled out as multiple mergers from different directions average out. The result, after billions of years of mergers, is a single, very massive galaxy, with a smooth, dynamically relaxed profile and a very extended halo of stars, many of which originally belonged to other galaxies. Here is the key concept. CD galaxies are, in this sense, cosmic cannibals. They are large because they have eaten other galaxies. The stars in their outer halo include stars that were born in many different parent galaxies, all of which were swallowed by the central galaxy at various times over the past 10 billion years. If you could somehow tag each star in IC 1101 with its galaxy of origin, you would find that the stars in the dense center tend to share a common origin in the original seed galaxy, while the stars in the diffuse halo come from a patchwork of dozens, possibly hundreds, of smaller galaxies that drifted in over cosmic time and were tidally disrupted before being absorbed into the central halo. The cathedral was built from quarry stones taken from many different surrounding villages. Here is the published estimate. Modern simulations of structure formation, including the illustrious TNG simulation and the Eagle simulation, both of which trace galaxy assembly across cosmic time, suggest that a typical CD galaxy in a rich cluster has acquired between 50 and 100 merged smaller galaxies over its history. The work of Van Dockum and his collaborators at Yale on the assembly histories of massive ellipticals, particularly Van Dockum 2010, has established that the bulk of the stellar mass growth in galaxies like IC 1101 came from minor mergers with smaller satellite galaxies, rather than from major mergers between equal-sized galaxies. The growth was incremental, slow, and persistent. Each individual merger added perhaps 1% of the central galaxy's mass. Over billions of years, the percentages added up. Here is what this implies about IC 1101 specifically. IC 1101, sitting at the center of one of the richest galaxy clusters known to astronomy, has had access to a particularly large reservoir of smaller galaxies to absorb over its history. The Abell 2029 cluster contains roughly 2,000 member galaxies, distributed across a region perhaps 15 million light-years across. Over the past 10 billion years, dozens of those smaller galaxies have spiraled inward through gravitational dynamical friction and merged into the central galaxy. Each one contributed its stars to IC 1101's growing halo. The result is the supergiant elliptical we observe today, a galaxy whose mass and size are not the result of a single dramatic event, but of a long, patient accumulation, like the slow assembly of a cathedral over centuries. Here is the slightly subtle point about how mass accretes. Cosmological simulations consistently show that the bulk of the stellar mass growth in CD galaxies happens through what astronomers call dry mergers between galaxies that have already exhausted most of their cold gas. When two gas-rich galaxies merge, the gas can collapse and produce a burst of new star formation. When two gas-poor galaxies merge, no new stars form, and the merged remnant is simply the sum of the two original stellar populations. CD galaxies like IC 1101 grow primarily through dry mergers, especially in the late stages of their assembly history. The result is that the galaxy's stellar population is dominated by stars that were formed elsewhere, in smaller galaxies, billions of years before they were absorbed. The cathedral, in this respect, is not a building where new stones are being quarried locally. It is a building where stones quarried elsewhere, long ago, are being added one by one. Here is the significance of the dry merger picture. Because most of the growth happens through dry mergers, IC 1101's central regions are dominated by the original seed galaxy's stellar population, which was formed during the very early universe. Its outer halo is dominated by the populations of merged satellite galaxies which formed at various times during the past 10 or 12 billion years, but which were themselves dominated by old stars at the time of merging. The end result is a galaxy whose entire stellar population is, on average, very old, even though the galaxy itself has been continuously growing through merging throughout its history. The age of the stars and the age of the galaxy as a whole are not the same thing. The galaxy is in a sense much older than any individual star within it would suggest, because the stars are mostly the stars that originally formed in smaller systems before being incorporated. Part 4. What IC 1101 actually is. Here is the demographic profile. IC 1101, by the best modern measurements, has a total stellar mass somewhere between 100 trillion and 400 trillion solar masses. The exact figure depends on how much of the diffuse outer halo you count as part of the galaxy and on how much of the dark matter halo you include. By comparison, our Milky Way has a stellar mass of roughly 50 to 70 billion solar masses. The total mass of IC 1101, including dark matter, is on the order of 100 quadrillion solar masses. That is 100,000 trillion. It is the kind of mass scale where ordinary intuition simply does not apply. There is no human experience of this kind of magnitude. There is only the arithmetic. Here is what those stars look like. Almost all of the stars in IC 1101 are old. The mean age of the stellar population is somewhere between 10 and 12 billion years, which means that essentially all of the stars in IC 1101 were formed during the first 3 billion years after the Big Bang. There is very little ongoing star formation in IC 1101 today. The galaxy has, in astronomical terms, gone red and dead. Most of the bright young blue and white stars that mark active star formation have lived out their few million-year lifespans long ago and have either become black holes, neutron stars, or white dwarfs. The visible light from IC 1101 is dominated by the cool red light of old red giant stars and red dwarf stars, with their characteristic peaks in the longer wavelengths of visible light. The galaxy looks, in colour photographs, distinctly orange-red, like the light of a distant fire seen through fog. Here is what the metallicity tells us. The chemical composition of IC 1101 stars, measured through careful spectroscopic observations, is on average enriched relative to the primordial composition of the early universe. The galaxy's stars contain heavier elements like carbon, nitrogen, oxygen, magnesium, and iron at levels that are roughly comparable to or somewhat higher than the levels in the Sun. This is consistent with the picture that most of IC 1101 stars formed during the first few billion years of cosmic history, when several generations of supernovae had already enriched the gas in the early universe. The metallicity is not uniform across the galaxy. The central regions show higher metallicities than the outer halo, consistent with the picture that the central regions formed first, from gas that had already been somewhat enriched, and the outer halo accumulated later through the merging of smaller satellite galaxies that had less enrichment of their own. The metallicity gradient observed in many CD galaxies is one of the cleanest pieces of evidence that the central regions and the outer halo had different formation histories. Here is why old galaxies look red. Stars at different stages of their lives produce different mixes of light. Young massive blue stars produce most of their energy at short wavelengths in the blue and ultraviolet. Old low-mass stars, particularly the red giants that result when low-mass stars exhaust their core hydrogen and expand, produce most of their energy at longer wavelengths, in the red and near infrared. A galaxy whose stellar population is dominated by old stars will, accordingly, appear red. A galaxy with active ongoing star formation will appear bluer because of the contribution from young massive stars. IC 1101 is overwhelmingly old. It accordingly appears overwhelmingly red. The colour itself encodes the age. Here is what IC 1101 looks like when you actually point a telescope at it. From Earth, at 1 billion light-years, IC 1101 appears as a small, faint, smooth, elliptical glow on photographic plates. There are no spiral arms because IC 1101 is not a spiral galaxy. There are no obvious dust lanes because the gas content is very low. There are no obvious bright young blue stars because there is essentially no ongoing star formation. The galaxy is, visually, almost featureless. It is a smooth ellipse of red light with a brighter centre and a gently fading outer halo. The colour photograph emphasises the orange-red colour, the smoothness, the lack of dust, the lack of obvious internal structure. It is, in this sense, the most unremarkable-looking object you could imagine for a galaxy that holds 100 trillion stars. The dramatic structures of spiral galaxies, the gas-rich star-forming arms, the central bars, the dramatic dust lanes, all of those features are absent in IC 1101. What you see is what was built by 10 billion years of slow gravitational settling. A smooth, dynamically relaxed, dynamically old, dynamically finished stellar system. Here is the physical structure. IC 1101 has a triaxial shape, like a gently flattened oblate ellipsoid, with axis ratios of roughly 1 to 0.8 to 0.7. The galaxy is more elongated along one axis than the other two, but only slightly so. There is no sharp boundary between the galaxy's main body and its halo. Instead, the surface brightness profile follows what is called a de Vaucouleurs profile, named after the French-American astronomer Gérard de Vaucouleurs, who, in 1948, characterized the typical brightness profile of elliptical galaxies as a particular mathematical function. The de Vaucouleurs profile is steep near the center and gradually flattens further out, producing a smooth distribution of starlight that fades gradually into the surrounding cluster medium. IC 1101 follows this profile, but with an additional very extended outer component beyond the standard de Vaucouleurs fit, the diffuse halo that gives CD galaxies their characteristic name. Part 5. The black hole at the center. Here is the central object. At the dynamical center of IC 1101, like at the center of every massive galaxy ever carefully studied, there sits a supermassive black hole. The mass of this black hole, by the best modern estimates, is somewhere between 40 billion and 100 billion solar masses. The exact figure is uncertain because IC 1101 is far away, and direct dynamical measurements of black hole masses become more difficult at greater distances. But the central black hole of IC 1101 is, by all available measurements, one of the most massive black holes that has ever been characterized in detail. It is, in scale, in the same league as the central black hole of M87, the famous galaxy, whose black hole was the subject of the first direct image of a black hole's event horizon, captured by the Event Horizon Telescope and announced in 2019. M87's black hole is about 6.5 billion solar masses. IC 1101's central black hole is, by the most credible measurements, roughly 10 times more massive than M87's. Here is the scale comparison. A black hole of 100 billion solar masses has an event horizon that is approximately 300 billion miles across, which is roughly 50 times the size of our entire solar system out to Pluto. If our solar system were placed inside the event horizon of IC 1101's central black hole, the entire solar system, all the planets, all the comets, the entire heliosphere extending out to where the solar wind meets the interstellar medium would fit comfortably inside the event horizon with substantial room to spare. The black hole is, in physical extent, larger than the solar system. It is one of the largest individual structures in the known universe. Here is how astronomers measure the mass of such a black hole. The mass of a supermassive black hole is typically inferred from its gravitational effect on the surrounding material, either on the orbits of stars near the center or on the rotation of gas in the central regions of the galaxy. For nearby black holes like Sagittarius A star at the center of our own Milky Way, astronomers can directly measure the orbits of individual stars over the course of years to decades, and from those orbits derive the mass of the central object. For more distant galaxies like IC 1101, direct stellar orbit measurements are not yet possible. Instead, astronomers measure the velocity dispersion of stars in the central region, which in dynamical equilibrium is related to the central mass through what is called the M-sigma relation. The M-sigma relation, established by John Megorian, Carl Gebhardt, John Cormendy, Louis Ho, and others in the late 90s and early 2000s, ties the central black hole's mass to the velocity dispersion of stars in the surrounding bulge. For IC 1101, the velocity dispersion of stars in its central region is unusually high, around 350 miles per second. The corresponding black hole mass derived from the M-sigma relation is roughly 40 to 100 billion solar masses. Here is what such a black hole does day to day. The black hole at the center of IC 1101 is, despite its enormous mass, not currently active in the sense of accreting large amounts of matter and producing strong electromagnetic emission. It is, in technical terms, mostly quiescent. Some weak X-ray and radio emission has been detected from the center, indicating that there is a small ongoing flow of gas onto the black hole, but the rate is far below the kind of activity that would produce a quasar or a strong active galactic nucleus. IC 1101 is not a quasar. It is a galaxy whose central black hole has, after billions of years of growth, settled into a slow, quiescent phase. The black hole has, in effect, run out of nearby gas and dust to consume. It still grows, but slowly, on a timescale that is essentially geological in cosmic terms. Here is the methodological caution. The estimates of IC 1101's central black hole mass have substantial uncertainty bands, and different methods produce somewhat different central values. Some estimates, based on different velocity dispersion measurements or different sample populations, have suggested that the mass could be lower, perhaps as low as 10 billion solar masses, which is still a very large black hole, but on the lower end of the supergiant scale. Other estimates, based on different assumptions about the dark matter contribution to the central potential, have suggested values up to 200 billion solar masses. The best modern estimate, which represents a careful averaging across multiple methods, is somewhere in the 40 to 100 billion solar mass range. That is the figure I'm using throughout this evening's telling. But the technical literature includes a range of values, and the topic remains an active area of research. Here is the m-sigma context for the broader picture. The m-sigma relation between black hole mass and host galaxy bulge, velocity dispersion, was first noted in the late 1990s by John Magorian and his collaborators. The relation was sharpened and refined by Carl Gebhardt and his collaborators in 2000 and the early 2000s, working at the University of Texas. The picture that emerged after roughly 2 decades of careful work was that essentially every massive galaxy hosts a central, supermassive black hole whose mass is tightly correlated with the velocity dispersion of stars in the bulge. The relation has scatter, but the scatter is small enough that the velocity dispersion alone is a useful predictor of black hole mass, even when no direct dynamical measurement is available. The work of John Cormandy and Louise Ho, particularly their 2013 review article in the Annual Review of Astronomy and Astrophysics, titled Co-Evolution of Supermassive Black Holes and Their Host Galaxies, summarized the state of the field at that time. Their review remains, 10 years later, the foundational reference for thinking about the masses of supermassive black holes in galaxies that have not been individually measured. Here is the deeper point about what such a black hole means. A supermassive black hole of 100 billion solar masses is, in its own right, one of the most extreme single objects in the visible universe. Its event horizon is larger than the entire solar system. Its gravitational influence reaches out across the central regions of the galaxy and shapes the orbits of stars within roughly 1,000 light-years of the center. The energy that has been released over its lifetime, through gradual accretion and through occasional bursts of activity, is somewhere on the order of 10 to the 63 ergs. That is a number with 63 zeros expressed in the units that astronomers use for energy. It is approximately the energy that would be required to lift the entire mass of the Milky Way's stars to escape velocity from the galactic potential well. The black hole at the center of IC 1101 has, over its history, processed energy on the scale of an entire galaxy's worth of binding energy. That is, in some sense, what defines a supermassive black hole. The energy processed is on the same scale as the energy of the host galaxy itself. Part 6. The galaxy Cannibal. Here is the long history of IC 1101. The galaxy did not begin as a galaxy of 100 trillion stars. It began, roughly 12 billion years ago, as a relatively modest galaxy, perhaps 10 times larger than the Milky Way at most, sitting at the center of a forming galaxy cluster. Around it, in the surrounding cluster, were dozens or hundreds of other galaxies, most of them smaller, drifting on slow orbits through the cluster's gravitational well. Over the next 12 billion years, the central galaxy grew. It grew through a process called dynamical friction, by which smaller galaxies, when they pass close to a more massive central galaxy, experience a frictional drag from the gravitational interactions with the surrounding stars and gas. Their orbits gradually decay. They spiral inward over hundreds of millions of years, Eventually, they merge with the central galaxy. Here is the metaphor that sits at the heart of this evening's telling. IC 1101 is the Cathedral of Stars, a vast, slow cathedral built brick by brick from the stones of every smaller galactic structure that drifted close enough to be quarried. The bishops of this cathedral are the supermassive black holes that came in with the merging galaxies, eventually settling into the cathedral's central altar. The walls and buttresses of this cathedral are the diffuse halo of old stars that came from those merged galaxies, now settled into the slow gravitational equilibrium of the merged whole. The nave is the dense central region where the original seed galaxy's stars are concentrated. The cathedral has been growing for 10 or 12 billion years. It is still growing today, though much more slowly than in its early epochs. Let me sit with that for a moment. The light arriving in the JWST mirror tonight, the photons that have travelled across 1 billion light-years of space from IC 1101 to reach Earth, are photons that were emitted by stars whose own birthplaces, in many cases, were not even within the galaxy itself. They were born in dwarf companions, in nearby ellipticals, in groups of merging galaxies that were absorbed into the central body long before the photons we see were emitted. The light we see tonight is the cumulative biography of dozens of disappeared galaxies. Each of those galaxies, in its time, was a complete and self-contained cosmic structure. Each had its own history, its own population of stars, its own dark matter halo. Each was, in the moment before absorption, a galaxy. Then it merged. Then it ceased to be a separate object. Then its stars became part of the cathedral. The light we see is, in this sense, a memorial. The cathedral is built from the stones of the disappeared. Here is the technical mechanism. Dynamical friction, the process by which smaller galaxies spiral inward toward a more massive central galaxy, was first carefully analysed by the Indian-American astronomer Subramanian Chandrasekhar in 1943 in a paper titled Dynamical Friction. Chandrasekhar showed that a massive object moving through a sea of smaller particles experiences a drag force because the smaller particles are gravitationally pulled into a wake behind the massive object, and that wake, being denser than the surrounding medium, pulls back on the moving body. In a galaxy cluster, smaller galaxies passing through the dense central region experience this drag from the surrounding stellar and dark matter distribution. Their orbits gradually decay. They spiral inward, losing energy to the surrounding medium until they eventually merge with the central galaxy. The whole process is slow but inexorable. Here is what we observe today as evidence of this history. Modern deep imaging of IC 1101 reveals a number of subtle features that are interpreted as evidence of ongoing or recent mergers. There are faint shells of light around the galaxy, visible only with very deep imaging, which are interpreted as the remnants of recent merger events. The shells form when a smaller galaxy is tidally disrupted as it falls into the central galaxy, and its stars are spread out into a thin, shell-like distribution that gradually phase mixes into the central halo. There are also faint streams of stars, visible only to the most sensitive modern surveys, which trace the dissolved orbits of smaller galaxies that were swallowed within the past few billion years. These features, taken together, paint a picture of a galaxy that has been steadily growing through merging with its neighbours and which is still growing today, though at a slower pace than in its early epochs. Here is the timescale of dynamical friction. in concrete terms. A galaxy of, say, 1 billion solar masses falling toward IC 1101 from a distance of 1,000,000 light-years takes roughly 5 billion years to spiral in through dynamical friction and merge with the central galaxy. The exact timescale depends on the mass of the infalling galaxy, the mass distribution of IC 1101 and its surrounding cluster, and the orbital geometry of the infall. But for typical infalling satellites, the timescales are billions of years, not millions. The mergers do not happen suddenly. They unfold slowly in cosmic terms, with each spiraling galaxy taking longer to merge than the entire history of complex life on Earth. From the perspective of any observer with a human lifespan, the cathedral appears stationary. From the perspective of cosmic time, it is constantly being renovated. Here is the published estimate refined. Modern measurements of stellar masses for CD galaxies using a combination of optical and infrared photometry calibrated against stellar population synthesis models have somewhat refined the original estimates of IC 1101's stellar mass. The most current best estimates, from work by Roberto Saglia and his collaborators in Munich, by Qian Peng and his collaborators at the National Optical Astronomy Observatory, and by similar groups elsewhere, place IC 1101's total stellar mass within a factor of 2 of 100 trillion solar masses. The uncertainty, while still significant, has narrowed substantially since the original Uson 1991 paper. Each new generation of imaging instruments with deeper sensitivity and better photometric calibration has helped to pin down the central estimate. The cathedral's mass is well known, even if its exact boundary remains a matter of where you choose to draw the line. Here is the cumulative picture that simulations produce. The Illustris TNG simulation run by Mark Vogelsberger, Annalisa Pilipich, Federico Marinacci, and their collaborators traces the assembly of a representative volume of universe over 13 billion years of cosmic time. The simulation includes prescriptions for star formation, supernova feedback, AGN feedback, and dark matter dynamics, and produces synthetic galaxy clusters with a level of detail that is comparable to the real observations. For galaxy clusters of the mass of Abell 2029, the simulation predicts that the central galaxy has, over its history, accreted roughly 50 to 100 separate satellite galaxies, with the most recent significant mergers happening within the past few billion years. The prediction matches the observed properties of IC 1101 reasonably well, though there are detailed discrepancies in the inner brightness profile and the distribution of stellar metallicities that are still being worked through. The simulation is a useful guide, not a final answer. Part 7. The Old Red Galaxy Problem. Here is the puzzle. IC 1101's stellar population is overwhelmingly old. The stars are mostly between 10 and 12 billion years old. There is essentially no ongoing star formation. This is, on the face of it, a puzzle. Stars in galaxies form from gas. If a galaxy is not actively forming stars today, it is because it has either run out of gas, or because its gas is too hot to collapse into new stars, or because some other mechanism is preventing star formation. Why has IC 1101 stopped forming stars? Here is the working answer. The current best understanding is that IC 1101 stopped forming stars several billion years ago because of a combination of 3 mechanisms. The first is what astronomers call quenching by mass. As galaxies grow more massive, the gravitational potential well at their center deepens, and the gas that falls into the center becomes more strongly heated by gravitational compression. At some critical mass, the heating overwhelms the ability of the gas to cool radiatively, and the gas remains too hot to collapse into new stars. This mechanism, called virial shock heating, was developed by Avishai Dekel and his collaborators in the early 2000s and has been extensively studied in the subsequent literature. IC 11.1 is well above the mass threshold where virial shock heating becomes effective. Its hot gas halo, observed in X-rays by satellites like Chandra and XMM Newton, has a temperature of millions of Kelvin, far too hot to collapse into new stars without first cooling. Here is the second mechanism. The second mechanism is what astronomers call active galactic nucleus feedback. The supermassive black hole at the center of a galaxy, when it accretes gas and dust, produces enormous amounts of energy that can be ejected back into the surrounding galaxy in the form of jets, winds, and radiation. This feedback can heat the surrounding gas, expel it from the galaxy, or both, preventing further star formation. AGN feedback has been extensively studied by groups including the work of Andrew Fabian and his collaborators at Cambridge, who have particularly studied the feedback from the central black holes of cluster central galaxies like IC 11.1. The Fabian group's work, using deep X-ray observations of cluster central galaxies, has identified clear evidence of AGN feedback in many systems, including evidence of cavities in the hot gas halo that were inflated by past AGN activity. IC 11.1 in earlier epochs would have experienced significant AGN feedback that helped to shut down its star formation. Here is the third mechanism. The third mechanism is what astronomers call Ram pressure stripping. As galaxies move through the hot intracluster gas at high velocities, the gas in their interstellar medium is pushed back by the Ram pressure of the surrounding cluster gas. For smaller galaxies in clusters, this can effectively strip the cold gas from the galaxy, removing the raw material for star formation. For IC 11.1 itself, sitting at the center of the cluster and moving relatively slowly compared to the cluster as a whole, Ram pressure stripping is less important than for satellite galaxies. But the satellite galaxies that fell into IC 11.1 over the past 10 billion years had their gas stripped before they merged, contributing fewer fresh raw materials for star formation than they would have if they had remained isolated. Here is what these three mechanisms produce together. Together, virial shock heating, AGN feedback, and Ram pressure stripping have produced a galaxy that is essentially gas-poor, with a hot gaseous halo too hot to cool, and a satellite galaxy supply that has been gas-stripped before merging. The galaxy has, accordingly, stopped forming new stars. The stars that exist in IC 11.1 today were almost all born during its early epochs, when the galaxy was still gas-rich and actively forming stars. They are the stellar memorial of a forgotten era of star formation. The cathedral has long since stopped accepting new stones. The bricks that exist are the bricks that will exist for the rest of cosmic history. Here is what this implies for the future. Over the next 10 billion years, the stars in IC 11.1 will continue to age. The most massive stars are already long gone, having lived out their few million-year lifespans during the first billion years of the galaxy's history. The intermediate mass stars are, on average, in the late phases of their main sequence lives or beginning to evolve onto the red giant branch. The lowest mass stars, the red dwarfs, will continue burning hydrogen at very slow rates for trillions of years. As the galaxy continues to age, its color will gradually shift even further toward red as the bluer stars fade and the redder stars come to dominate the integrated light. Eventually, perhaps trillions of years from now, the galaxy will fade beyond detectability for any external observer. Its stars will dim, its red dwarfs will exhaust their hydrogen one by one. The cathedral will, in the very long run, fall dark. Part 8. The cluster around it. Here is the surrounding context. IC 1101 sits at the centre of the Abell 2029 cluster, which is one of the richest galaxy clusters within 1 billion light-years of Earth. The cluster contains roughly 2,000 member galaxies distributed across a region perhaps 15 million light-years across, and is held together by an enormous gravitational well filled with hot gas, dark matter, and the baryonic mass of the member galaxies themselves. The cluster's total mass, by the best estimates, is on the order of 1 quadrillion solar masses. That is 1,000 trillion solar masses. The cluster, taken as a whole, is one of the most massive gravitationally bound structures in the local universe. Here is the catalogue context. The cluster's name, a 2029, comes from the Catalogue of Galaxy Clusters published by the American astronomer George Abell in 1958. Abell, working with photographic plates from the Palomar Observatory Sky Survey, catalogued thousands of galaxy clusters across the visible northern sky. His catalogue, the Abell Catalogue of Clusters of Galaxies, has been the foundational reference for galaxy cluster studies ever since. Each cluster in the Abell catalogue is identified by its catalogue number, with brighter and richer clusters generally being given lower numbers. Abell 2029 is in the upper end of the catalogue numbers, but it is among the richest and most massive of the clusters in the catalogue, ranking near the top in terms of total galaxy count and total mass. Here is what the cluster looks like. From Earth, the Abell 2029 cluster appears as a concentrated cloud of small, faint, elliptical and lenticular galaxies, with IC 1101 at the centre as the brightest and most extended object. The cluster is at a redshift of about 0.077, meaning that the universe has expanded by a factor of about 7.7% since the light from the cluster left it. The light arrived in our telescopes after travelling for roughly 1 billion years. The cluster is, in cosmic terms, relatively nearby. There are far more distant galaxy clusters that are routinely studied, but Abell 2029 is close enough that detailed observations of individual member galaxies are practical, while still far enough that the cluster sits in a relatively well-relaxed, dynamical state. Here is the structure of the cluster gas. The space between the galaxies in Abell 2029 is filled with a hot, gaseous medium called the intra-cluster medium. The temperature of this gas, observed in X-rays by Chandra and XMM Newton, is about 80 million Kelvin. It is one of the hottest natural plasma environments known. The gas is so hot that in any given region of the cluster, hydrogen and helium atoms have been completely ionized, and electrons are bouncing around at high speeds, producing the observed X-ray emission through a process called Bremsstrahlung. The total mass of the hot intra-cluster gas in Abell 2029 is roughly 10% of the cluster's total mass, with the remaining 90% being dominated by dark matter and the stellar mass of the member galaxies. Here is the additional historical observation. The Einstein X-ray Observatory, launched in 1978 and operating until 1981, was the first imaging X-ray satellite. It produced the first X-ray maps of galaxy clusters, including Abell 2029, establishing that the spaces between cluster galaxies are filled with hot X-ray emitting gas. Before Einstein, the existence of the hot intra-cluster medium had been inferred from indirect observations but never directly imaged. Einstein's images, while crude by modern standards, were the first to show that galaxy clusters are not just collections of galaxies in empty space, but are embedded in vast clouds of million-degree gas that emit copiously in X-rays. The discovery transformed the understanding of galaxy clusters as gravitationally bound systems with their own thermodynamic structure. The line of work that began with Einstein continues today, 4.5 decades later, with Chandra and XMM Newton, and will continue with the next generation of X-ray observatories like the European-led Athena mission, planned for the late 2030s. Here is the named instrument context that's worth holding. The Chandra X-ray Observatory, launched in 1999, is one of NASA's flagship space telescopes. It produces X-ray images with sub-arc-second resolution, comparable in spatial precision to ground-based optical telescopes, but at X-ray wavelengths that ground-based instruments cannot detect. The European Space Agency's XMM Newton, also launched in 1999, complements Chandra with much higher photon collecting area, allowing detailed spectroscopy of fainter sources. Together, these two missions have, over the past 2 decades, mapped the X-ray emission from Abell 2029 and dozens of other galaxy clusters, producing a detailed picture of the temperature structure, the metallicity distribution, and the dynamical state of the intracluster gas. The work has been led in part by Andrew Fabian and his Cambridge collaborators, by Stefano Borgani and his Italian collaborators, and by Megan Donoghue and her American collaborators. The cumulative picture, after 20 years of careful observations, is of a hot, complex, thermodynamically rich, gaseous environment in which the central cluster galaxy is embedded. Here is the thermodynamic detail that matters. The hot intracluster gas in Abell 2029 is not in a perfectly relaxed thermal equilibrium. The gas density and temperature vary across the cluster in patterns that record the history of feedback from IC 1101's central black hole. There are visible cavities in the X-ray emission, regions of lower density gas that were inflated by past AGN-driven jets, pushing aside the cluster gas. There are also weak shock fronts, sharp transitions in temperature and density that record the propagation of energy from past AGN outbursts. The Andrew Fabian group, working primarily with Chandra observations, has identified multiple generations of cavities in Abell 2029, suggesting that the central black hole has gone through multiple cycles of activity over the past few billion years. Each cycle of activity injects energy into the surrounding gas, helps to maintain the gas at high temperature, and prevents the gas from cooling and collapsing into new stars. The feedback loop is, in a sense, self-regulating. The central black hole prevents the cluster gas from cooling, which prevents new gas from accreting onto the black hole, which keeps the AGN activity at a low and steady rate. Here is the deep observation point. The hot, intracluster gas in Abell 2029 has been mapped in detail by X-ray observations spanning decades, beginning with the Einstein Observatory in the late 1970s and continuing through the Chandra and XMM Newton missions in the 21st century. These observations have revealed a complex structure of cool cores, hot bubbles, and gas streamlines that record the history of feedback from IC 1101's central black hole and the merger history of the cluster as a whole. The cluster gas is not in a perfectly relaxed state. It shows evidence of recent and ongoing dynamical activity, including weak shock fronts, cavities inflated by past AGN activity, and asymmetries in the gas distribution that record past mergers between subclusters. Here is what the cluster tells us about IC 1101's history. The richness of the cluster, with 2,000 member galaxies, and the depth of the cluster's gravitational well, with 1 quadrillion solar masses of total mass, mean that IC 1101 has had access to an enormous reservoir of smaller galaxies to absorb over the past 10 billion years. The galaxies that fell in were, in many cases, fully formed and self-sustaining stellar systems before they were absorbed. They had their own stellar populations, their own dark matter halos, their own gas content. As they fell in, dynamical friction slowed their orbital motion, ram pressure stripping removed their cold gas, and tidal forces gradually pulled them apart. The remnants, stars, and dark matter were absorbed into IC 1101's halo. The cluster gas was enriched. Over time, the central galaxy grew, and the cluster around it became more concentrated and dynamically relaxed. Here is the comparison the cluster bears to other clusters. Abell 2029 is, by mass, comparable to the Coma cluster in the constellation Coma Berenices, the Perseus cluster in Perseus, and the Virgo cluster in Virgo. Each of these clusters has a central galaxy that is in its own way comparable to IC 1101. The central galaxy of the Coma cluster is NGC 4889, a CD galaxy with a central black hole estimated at more than 20 billion solar masses. The central galaxy of the Perseus cluster is NGC 1275, also known as Perseus A, which is a particularly active example with a strong central AGN producing visible jets. The central galaxy of the Virgo cluster is M87, the famous galaxy whose central black hole was the subject of the Event Horizon Telescope's first direct image. Each of these clusters has been studied in great detail. Each provides a partial check on the picture that IC 1101 also exemplifies. The picture refined across these multiple clusters is consistent. Every rich cluster has a central CD galaxy with a supermassive black hole embedded in a hot intracluster medium surrounded by hundreds to thousands of satellite galaxies and growing slowly through hierarchical merging. The pattern is universal among rich galaxy clusters in the local universe. Part 9. How far IC 1101 stretches. Here is the spatial scale in human terms. IC 1101 extends, on its most generous measurement, across roughly 6 million light-years from end to end. To get a feel for that scale, consider that the distance to the Andromeda Galaxy, our nearest large neighbour, is about 2.5 million light-years. So IC 1101 is in linear extent roughly 2.5 times the distance from the Milky Way to Andromeda. If the Milky Way and IC 1101 were placed side by side, with their centres separated by the standard distance to Andromeda, the outer halo of IC 1101 would extend most of the way across the gap to Andromeda. The galaxy would, in this hypothetical comparison, almost reach out and touch us. Here is the same scale in another comparison. The distance from the Sun to Proxima Centauri, the nearest star to our Sun, is about 4.2 light-years. The distance from one end of IC 1101 to the other is therefore roughly 1.5 million times the distance from the Sun to Proxima Centauri. If you somehow shrunk Proxima Centauri to be a single inch from the Sun, then IC 1101 would still be roughly 20,000 miles across at that scale. The galaxy is, in physical extent, beyond any meaningful human comparison. It is simply much larger than our intuition can comfortably grasp. Here is what light travelling within IC 1101 actually does. A photon emitted from one edge of IC 1101 would take roughly 6 million years to travel to the opposite edge. That is comparable to the time elapsed since the earliest hominids diverged from chimpanzees on the African savanna. A photon emitted at the moment our hominid ancestors split off from chimpanzees, if travelling across IC 1101, would still be in transit, having not yet reached the far edge. The galaxy is so large that the speed of light, which we are accustomed to thinking of as effectively infinite for human scale purposes, becomes a meaningful timescale within the galaxy itself. Here is the consequence for internal dynamics. The orbital periods of stars in IC 1101 are accordingly very long. A star at the outer edge of the diffuse halo, orbiting the galaxy's centre at a typical orbital velocity of perhaps 400 miles per second, takes about 10 billion years to complete a single orbit. That is comparable to the entire age of the galaxy itself. Stars in IC 1101's outer halo have, in many cases, completed only 1 or 2 orbits in their entire lifetime. The galaxy is, in this dynamical sense, only beginning to settle. Its outer regions are still partially in the process of dynamical relaxation. The cathedral is, in these very outermost reaches, still being polished. Here is the comparison with the cosmic web. The very largest scales of cosmic structure on which galaxy clusters like Abell 2029 sit are organized into a network called the cosmic web. The cosmic web consists of filaments, sheets, and voids, with the densest regions at the intersections of filaments. Galaxy clusters tend to form at these intersections, where multiple filaments of dark matter and ordinary matter come together. IC 1101's parent cluster sits at one such intersection. The cluster is connected, through filaments of intergalactic gas and dark matter, to other galaxy clusters tens of millions of light-years away. The whole structure of the local universe on the largest observable scales is organized into this filamentary web. Galaxy clusters like the one containing IC 1101 are the densest knots in the web. The voids between are largely empty. The picture, when assembled across surveys like the Sloan Digital Sky Survey, looks remarkably like a network of foam, with galaxy clusters at the foam edges and intersections and voids in the bubble interiors. The cathedral of IC 1101 is, in this larger picture, just one of many such cathedrals scattered across the cosmic web. Here is the dark matter component. The total mass of IC 1101, including the dark matter halo, is on the order of 100 quadrillion solar masses. About 95% of this mass is dark matter, with the remaining 5% being the visible stellar matter and the hot gas. The dark matter halo extends well beyond the visible stars, perhaps out to 10 million light-years from the centre. It is the dark matter halo that, in the modern picture of galaxy formation, provides the gravitational scaffolding on which the visible galaxy was assembled. Without the dark matter halo, the galaxy could not have formed in the first place. The visible cathedral is, in a sense, supported by an even larger, invisible structure that we can detect only through its gravitational effects. Here is the historical lineage of the dark matter idea. The American astronomer Vera Rubin, working at the Carnegie Institution in Washington, D.C. in the 1970s, established that the rotation curves of spiral galaxies could not be explained by the visible matter alone. Her observations, together with the earlier work of the Swiss-American astronomer Fritz Zwicky in the 1930s on the Coma cluster, established that galaxies and galaxy clusters must contain substantial amounts of unseen matter. Zwicky, in 1933, had measured the velocity dispersion of galaxies in the Coma cluster and found that the cluster contained far more mass than the visible galaxies could account for. He coined the term dunkle Materie, dark matter, to describe the missing mass. Rubin's work, 4 decades later, extended the same conclusion to individual galaxies. Today, the existence of dark matter is one of the best established results in modern astronomy, and the dark matter halo of IC 1101 is consistent with the same physics that has been observed in countless other galaxies and clusters. Here is the further inferential point. The total mass of Abell 2029, taking into account the visible galaxies, the hot intracluster gas, and the inferred dark matter, has been measured by multiple independent methods. The velocity dispersion of the galaxies, measured spectroscopically, gives one estimate. The X-ray temperature and density of the intracluster gas, in conjunction with the assumption of hydrostatic equilibrium, gives another. The gravitational lensing of background galaxies whose light passes through the cluster gives a third. The 3 methods agree, within their uncertainties, on a total cluster mass of roughly 1 quadrillion solar masses. The agreement is itself a confirmation of the underlying picture. 3 different physical phenomena derived from 3 independent observations all converge on the same total mass. That kind of cross-validation between methods that depend on entirely different physics is what builds confidence in modern astronomical measurements. Part 10. Why this matters for cosmology. Here is the cosmological role IC 1101 plays. The existence of galaxies as massive as IC 1101, sitting at the centers of rich clusters, is a strong test of our understanding of cosmic structure formation. The standard cosmological model, called lambda cold dark matter, or lambda CDM, predicts that structure forms hierarchically. Small structures form first, and gradually merge to form larger structures over cosmic time. The most massive galaxies in this picture should be the descendants of many smaller galaxies that have merged together over the past 10 or 12 billion years. IC 1101, as the brightest galaxy in the most massive cluster within 1 billion light-years of Earth, is exactly the kind of object that the standard model predicts should exist at the present cosmic epoch. The mere fact that IC 1101 exists, with its observed mass and size, is consistent with the predictions of lambda CDM. Here is the more subtle test. The detailed properties of IC 1101, its size, its mass, its stellar age distribution, its halo structure, its central black hole mass, provide a more demanding test of the model. Modern cosmological simulations, like the illustrious TNG simulation by Mark Vogelsberger and his collaborators, the Eagle simulation by Jup Shea and his collaborators, and the Fire simulation by Philip Hopkins and his collaborators, all attempt to reproduce the observed properties of galaxy clusters and their central galaxies. The simulations include detailed prescriptions for star formation, AGN feedback, dynamical friction, and dark matter dynamics. The match between simulation and observation for galaxies like IC 1101 is generally good, but not perfect. Particular discrepancies exist in the detailed shapes of brightness profiles, in the inferred dark matter distribution at the very center, and in the detailed history of mergers. Each discrepancy is a target for further refinement of the model, both by improving the observations and by improving the simulations. Here is the deeper point. IC 1101, like JD's GSZ 140 from our previous evening, is a probe of cosmic history, where JD's GSZ 140 is a probe of the very early universe. IC 1101 is a probe of the late accumulated structure of the universe. Both objects, in their different ways, place strong constraints on what we think we understand about cosmology. The fact that they are both broadly consistent with the standard cosmological model while still having particular features that test the model in detailed ways is itself the way that science makes progress. The model is not perfect. The model is not done. Each new observation, each new measurement refines the model further. Each individual galaxy that has been carefully studied contributes a data point to the picture. Here is what this implies about galaxy cluster studies more broadly. IC 1101 is a particularly extreme example, but the picture that emerges from studying it generalizes to galaxy clusters across the universe. Every rich galaxy cluster in the modern picture has a central cluster galaxy that has grown through hierarchical merging over billions of years. Most of the central cluster galaxies are old, red, and relatively quiescent. Most of them have very massive central black holes. Most of them sit at the bottom of deep gravitational potential wells filled with hot intracluster gas. The picture is not unique to IC 1101. IC 1101 is simply one of the most prominent and extreme examples of a general pattern of structure formation in the universe. Part 11. The dimming of red giants. Here is the long-term fate. Over the next 10 or 20 billion years, IC 1101 will continue to age. The stars that exist will continue to evolve. Most of the galaxy's red giants, which have already made the transition from the main sequence to the giant branch, will eventually shed their outer envelopes and become white dwarfs. White dwarfs are dense, compact remnants of low-mass stars supported against gravitational collapse not by ongoing fusion, but by the quantum mechanical pressure of degenerate electrons. They emit only the residual heat from their formation, gradually cooling over billions of years. Over the very long term, the population of luminous red giants in IC 1101 will gradually be replaced by a population of cooling white dwarfs. Here is what the galaxy will look like in the very deep future. Roughly 20 billion years from now, when the universe is itself perhaps 30 billion years old, IC 1101 will be a galaxy populated mainly by white dwarfs, neutron stars, brown dwarfs, and red dwarfs. The brightest stars will be the lowest mass red dwarfs, which can sustain hydrogen fusion in their cores for trillions of years. The galaxy will have shifted even further toward red, and its overall luminosity will have dropped substantially. By 100 billion years from now, even the red dwarfs will have begun to exhaust their hydrogen, and the galaxy will be even fainter. By 1 trillion years from now, the galaxy will be barely detectable in any optical band. The cathedral will be falling dark. Here is the controlled comparison. The Milky Way, our own galaxy, will go through a similar long-term fate. Our galaxy is younger than IC 1101 in the sense that it has more ongoing star formation, but our star formation rate is steadily declining. And within the next 10 billion years, our galaxy will likely also have shifted to a quenched state similar to IC 1101's current state. Our galaxy will, in the very long run, also become a fading red and dead galaxy, populated by white dwarfs, neutron stars, and red dwarfs. The pace will be different, but the ultimate trajectory is the same. The cosmic universe, on timescales of trillions of years, is steadily shifting toward a state of dim, cooling, stellar remnants. IC 1101 is simply ahead of the curve. Here is the cosmic context. The universe itself is expanding. The expansion is accelerating. Over very long timescales, distant galaxies will recede beyond our cosmic horizon, becoming permanently unobservable. The local volume of universe accessible to any observer will gradually shrink. Eventually, on timescales much longer than the lifetime of stars, even the cosmic background radiation will fade beyond detection. The universe will become, on extremely long timescales, a cold, dark place punctuated by isolated cooling stellar remnants. IC 1101, like every other galaxy, will be part of that long fade. Here is what continues. In the meantime, while we are still here, while the universe is still relatively young, while IC 1101 still has its visible red giants and its hot intra-cluster gas, and its supermassive central black hole, the galaxy is observable. We can study it. We can measure it. We can refine our understanding of how it formed and what it is doing now. The work continues year by year, decade by decade. Each new instrument adds another piece to the picture. Each new generation of astronomers refines what the previous generation observed. The cathedral is, in this sense, our cathedral too. We are part of the cosmic context that allows it to be observed at all. Here is the long-term timeline in concrete numbers. The universe is currently about 13.8 billion years old. The longest-lived stars in IC 1101, the lowest mass red dwarfs, will continue to burn hydrogen in their cores for approximately 10 trillion years from now. After that, even the red dwarfs will exhaust their fuel and begin to evolve into white dwarfs. The white dwarfs themselves will gradually cool over hundreds of billions of years, eventually radiating away their residual heat and becoming black dwarfs. Black dwarfs are entirely hypothetical at this point in cosmic history. The universe is not yet old enough to contain any. They are simply the projected end state of cooled white dwarfs, which the universe will eventually start producing in large numbers some hundreds of billions of years from now. By the time IC 1101 is dominated by black dwarfs, the universe will be roughly 100 trillion years old, perhaps somewhat more. At that point, the cathedral will have effectively gone dark. Here is the further long-term picture. Beyond the cooling of the stellar remnants, on timescales of tens of trillions to hundreds of trillions of years, the gravitational dynamics of the galaxy itself will continue to evolve. Some stellar remnants will be ejected from the galaxy through chance gravitational interactions. Others will be captured by the central, supermassive black hole. The galaxy as a coherent object will gradually evaporate, with most of its mass being either swallowed by the central black hole or scattered into intergalactic space. By a quadrillion years from now, the galaxy will likely no longer exist as a recognizable structure. The central black hole, having absorbed most of what was once the galaxy, will be even more massive than it is today, but the surrounding stellar system will have largely dispersed. Part 12. The catalogue ancestors. Here is the long arc of human cataloguing. IC 1101 was first noted by William Herschel in 1790, but it took 2 centuries before the galaxy's true nature was understood. Herschel, in his time, did not know that the smudge of light he was looking at was a separate galaxy, a self-contained stellar system, far beyond the bounds of our own. The concept of galaxies as separate stellar systems would not be established until well into the 20th century, when Edwin Hubble, working at the 100-inch telescope at Mount Wilson Observatory, established that the so-called spiral nebulae were galaxies separate from our own. Hubble's work, particularly his 1925 and 1929 papers establishing extragalactic distances using Cepheid variable stars, transformed the entire field of astronomy. Before Hubble, the universe was thought to be largely the Milky Way alone. After Hubble, the universe was understood to be a vast, expanding collection of galaxies, of which the Milky Way was only one example. Here is the catalogue lineage. Herschel's original catalogue of nebulae, published in 1786 and 1789, contained 2,500 objects. His son, John Herschel, later extended the catalogue, and the combined Herschel catalogue served as the basis for John Dreyer's new general catalogue of nebulae and clusters of stars, published in 1888, which contained roughly 7,800 objects. Dreyer's later index catalogue, published in 1895, with a supplement in 1908, added another 5,000 objects. IC 1101, as a member of the index catalogue, was added in this 19th century cataloguing effort. The number 1101 in its name indicates that it was the 1101st object added in the supplemental catalogue. Here is the Hubble context that turned smudges into galaxies. Edwin Hubble, working at the 100-inch Hooker telescope at Mount Wilson Observatory in California in the mid-1920s, established that the so-called spiral nebulae were galaxies separate from our own. Hubble's 1925 paper, in which he identified Cepheid variable stars in the Andromeda Galaxy, and used the period luminosity relation discovered by Henrietta Swan Leavitt to estimate Andromeda's distance, was the foundational work of extragalactic astronomy. Before Hubble, the universe was thought to be largely the Milky Way alone, with the spiral nebulae perhaps being smaller satellite systems within or near our own galaxy. After Hubble, the universe was understood to be a vast, expanding collection of galaxies. His subsequent 1929 paper, establishing the relationship between the recession velocity of galaxies and their distance, established that the universe was expanding. The combination of these two papers transformed the entire field of astronomy and gave the catalogues of Herschel and Dreyer a new significance. The smudges were not nebulae, they were galaxies, each as large or larger than our own. Here is the deeper irony of the catalogue numbers. The numbering of objects in the index catalogue, including the number 1101 for our galaxy, reflects nothing about the object itself. It reflects only the order in which Dreyer happened to add it to his supplemental catalogue. Earlier numbered IC objects are not larger or more interesting than later numbered ones. The numbers are arbitrary positional labels. Yet for IC 1101, the catalogue number has become inseparable from the object's identity. Astronomers refer to IC 1101 by its number, because the number is the unique identifier in the literature. Most galaxies have only a catalogue number. Only the most prominent few have proper names like Andromeda, or the Sombrero, or the Whirlpool. IC 1101, despite being one of the largest galaxies in the visible universe, has only its catalogue number to identify it. The cathedral is unnamed except by accident of cataloguing. Here is the cluster cataloguing context. Galaxy clusters, as a category of astronomical objects, were first systematically catalogued by George Abell, working at the Palomar Observatory in California in the 1950s. Abell's 1958 catalogue of clusters of galaxies, published in the Astrophysical Journal Supplement, listed roughly 2,700 clusters across the visible northern sky. His method was to identify regions of the sky where the local density of galaxies was significantly higher than the surrounding average, using photographic plates from the Palomar Observatory Sky Survey. His catalogue has been the foundational reference for galaxy cluster studies for the past 65 years. Abell 2029, the cluster containing IC 1101, is a relatively rich cluster in his catalogue, with an Abell richness class of 2, indicating roughly 50 to 79 member galaxies in the central concentration. Here is the modern context. Modern catalogues of galaxy clusters, particularly those produced by the Sloan Digital Sky Survey and the European Space Agency's Planck mission, contain tens of thousands of clusters at much fainter magnitudes than Abell's original catalogue. Each cluster, when carefully studied, reveals the same broad picture: a central galaxy, often a CD galaxy, surrounded by smaller member galaxies embedded in a hot, gaseous halo, with a dark matter halo extending well beyond the visible stars. IC 1101 is simply one of the more extreme examples of this general pattern. There are perhaps 100 or 200 galaxy clusters in the local universe with central galaxies as massive as IC 1101. There are thousands more with central galaxies in the same general class, but with somewhat lower mass. Here is the deeper cataloguing point. The arc from Herschel in 1790 to the modern Sloan survey involves more than 2 centuries of patient observation, careful cataloguing, and gradually deepening understanding. Each generation has built on the work of the previous one. Herschel's smudges became Hubble's galaxies. Hubble's galaxies became Abell's clusters. Abell's clusters became the templates against which modern cosmological simulations are tested. The catalogue is, in this sense, alive. It grows, it is refined. Each new entry adds another piece to the picture of what the universe contains. The cathedral of stars that is IC 1101 has been, in this long process of cataloguing, slowly understood. From a smudge of light to a galaxy, to a member of a cluster, to one of the most massive single objects in the local universe. Part 13. Where to look. Here is how to find IC 1101 in the sky. The galaxy is in the constellation Serpens, specifically in the head of the serpent, which is in the spring sky in the northern hemisphere. The constellation Serpens in classical mythology was the snake handled by Ophiuchus, the serpent-bearer, and is one of the few constellations split into 2 non-contiguous parts: Serpens caput, the head, and Serpens cauda, the tail. IC 1101 is in Serpens caput, the head portion of the constellation. The constellation rises in the eastern sky in the late evening in spring and is visible most of the night through summer. From mid-northern latitudes, Serpens passes nearly directly overhead in the late evening of late spring. Here is some of what you can already see in that direction with the unaided eye. The brightest stars in Serpens caput include Unukalhai, the alpha star of the constellation, a magnitude 2.6 orange giant, about 74 light-years from Earth. Beta Serpentis, a hot blue-white main sequence star about 155 light-years away. Gamma Serpentis, a yellow-white subgiant about 36 light-years away. Several other stars of magnitude 3 and 4 mark out the recognizable shape of the serpent's head. These foreground stars are, by cosmic standards, almost on top of us. They are within a few hundred light-years. Beyond them, in the same direction in the sky, sits IC 1101, 1 billion light-years away, completely invisible to the unaided eye, but present in that line of sight. The contrast between what is easily visible and what is actually most cosmically significant is, in this case, extreme. Here is the practical observability. IC 1101 is at right ascension 15 hours and 10 minutes and declination plus 5 degrees and 45 minutes in the head of Serpens. Its apparent magnitude is around 14.7, which is well below the threshold for the unaided eye and significantly below the threshold for amateur telescopes of moderate size. To actually see IC 1101 visually requires a telescope with at least a 16-inch aperture, a clear, dark sky away from light pollution, and patience. Even in such a telescope, IC 1101 will appear as a small, faint, smooth elliptical glow, indistinguishable from many other distant elliptical galaxies. The faint outer halo that gives the galaxy its remarkable size is not visible in any amateur instrument. The full extent of IC 1101 is only visible in long exposure, deep imaging from professional telescopes. Here is what that means for the typical amateur. Most amateur astronomers will never see IC 1101 directly. The galaxy is simply too faint and too distant, but it is, in some sense, accessible to the imagination. When you look at the constellation Serpens on a clear spring evening, the head of the serpent contains, at one specific point about 1 billion light-years beyond, the largest single galaxy in the visible sky. The light from IC 1101 is arriving at Earth right now. Some of those photons are reaching the eyes of every observer who looks up in that direction, even though the galaxy itself is too faint for any naked eye perception. The photons are present. The galaxy is observable in principle. It is just that the photons are too few to register on the human retina without the help of a sufficiently large telescope. Here is the broader point about observability. Many of the most cosmically significant objects in the universe are completely invisible to the unaided eye: distant quasars, the cosmic microwave background, faint dwarf galaxies in the local group. Most galaxies beyond the local group, in fact. We perceive only a tiny fraction of what is out there. Modern astronomy is, in this respect, a process of artificially extending our senses with instruments that can detect what our biology alone cannot. IC 1101, the largest single galaxy known to astronomy, is one of those objects. Its existence and properties have been known for 2 centuries, but seeing it directly remains the privilege of professional observatories. For the rest of us, knowing about it is a matter of trust in the careful work of professional astronomers across many decades. Here is the modest comfort. There is, however, something quietly satisfying about being able to point to a small region of the sky and say, in that direction, 1 billion light-years away, sits a galaxy of 100 trillion stars. Whether or not we can see it directly, it is there. It has been there for 10 billion years. It will be there, slowly fading, for at least another 10 billion. The constellation that contains it, Serpens caput, has been a recognized pattern of stars for at least 3,000 years since the Babylonian astronomers first noted it. The stars of the constellation, which look like a single coherent shape from Earth, are themselves at varying distances of dozens to hundreds of light-years from us. They are foreground objects. Behind them, far behind them, is the region of sky where IC 1101 sits. The constellation is, in this sense, a window, a reference frame for finding our way to the galaxies beyond. Here is the sociological and cultural footnote, the kind of long-term cosmic projection that I have just walked through, in which the universe gradually becomes a cold, dark place, punctuated by isolated, cooling stellar remnants, is a picture that has been worked out in detail by astronomers including Fred Adams and Greg Laughlin in their 1997 reviews of modern physics paper titled A Dying Universe, and developed further in their 1999 book, The 5 Ages of the Universe. The framework provides a coherent picture of the very long-term future of cosmic evolution, dividing it into 5 eras based on the dominant physical processes. We are currently in the stelliferous era, the era of stars. After the stelliferous era will come the degenerate era, dominated by stellar remnants. Then the black hole era, in which stellar remnants have decayed and only black holes remain. Then the dark era, after the black holes themselves have evaporated through Hawking radiation. The framework is speculative for the latest eras, but is grounded in well-understood physics for the stelliferous and degenerate eras. IC 1101 will move from the late stelliferous to the degenerate era over the next 10 to 100 billion years. The cathedral, in this scheme, is just beginning the long shift toward becoming a graveyard of cooling remnants. Part 14. Coming Home. Here is the long arc of the story. We did not set out to find a galaxy of 100 trillion stars. We set out in the 18th century to catalogue the faint smudges of light visible in the eyepieces of growing telescopes. We did not know what those smudges were. We could not have known. The categories that would eventually let us understand them: galaxies as separate stellar systems, galaxy clusters as gravitationally bound concentrations of galaxies, dark matter halos, supermassive black holes, would not be established for another century or more. The cataloguing came first, the understanding came later. The ancestors of modern astronomy were sitting at their telescopes in cold observatories under dark skies, simply noting what they saw. The picture they were assembling, without yet knowing what the pieces meant, was a picture that would eventually reveal one of the largest single objects in the known universe. Here is what happened, slowly, over 2 centuries. Herschel's smudge became Dreyer's catalogue entry. Dreyer's catalogue entry became, after Hubble's 1920s work on extragalactic distances, a galaxy. The galaxy became, after Abell's 1950s cluster catalogue, the central galaxy of a rich cluster. The central galaxy of the cluster became, after Uson, Boughn and Kuhn's 1991 science paper, a supergiant elliptical of unprecedented size. The supergiant elliptical became, after the careful work of dozens of subsequent astronomers, a probe of structure formation, a test of cosmological models, a window into the deep history of the universe. The same object, IC 1101, has played all of these roles over time. The object has not changed. Our understanding has changed. The cathedral has revealed itself, brick by brick, as we have learned how to look. Here is the consensus picture today. IC 1101, by the best modern measurements, is one of the largest individual galaxies that has been carefully measured in the visible universe. It contains roughly 100 trillion stars, distributed in a smooth elliptical halo that extends from a dense center out to between 400,000 and 6 million light-years across, depending on which contour you choose to define the boundary. It hosts, at its center, a supermassive black hole of perhaps 40 to 100 billion solar masses. It sits at the center of the Abell 2029 cluster, one of the richest galaxy clusters in the local universe, which contains roughly 2,000 member galaxies and 1 quadrillion solar masses of total mass. It has grown over the past 10 or 12 billion years through the absorption of dozens of smaller galaxies that drifted into its gravitational well. It has stopped forming new stars several billion years ago and is now slowly fading toward eventual death. Here is the comparison with our own galaxy. The Milky Way, our home galaxy, is by comparison a relatively modest spiral. It contains perhaps 2 to 400 billion stars, distributed in a flattened spiral disk, perhaps 100,000 light-years across, with a central bulge and a dark matter halo extending another few 100,000 light-years. Our galaxy is still actively forming new stars at a modest rate of perhaps 1 to 2 solar masses per year. Our central black hole, Sagittarius A star, has a mass of about 4 million solar masses, which is far less than IC 1101's central black hole. By every measure, the Milky Way is smaller, younger, and more dynamic than IC 1101. We are not, in the cosmic context, an extraordinary galaxy. We are a typical example of a moderately large spiral. Here is the comparison with our previous evening's object. From our previous evening, JD's GS Z140, the most distant spectroscopically confirmed galaxy is a probe of the very early universe. It is a small, irregular, actively star-forming galaxy at a redshift of 14.32, observed at an epoch when the universe was only 290 million years old. By contrast, IC 1101 is a probe of the late accumulated structure of the universe. It is a massive, smooth, quenched elliptical at a redshift of just over 0.07, observed at an epoch when the universe is 13.8 billion years old. The two galaxies bracket the cosmic timeline of structure formation. JD's GS Z140 represents the seedlings of structure. IC 1101 represents the cathedrals that grew from them eventually over more than 10 billion years. Both are the same physics, applied at very different epochs. Here is what this evening's telling has tried to do. We have walked through how astronomers measure galaxy sizes, what CD galaxies are, how IC 1101 was assembled through cosmic cannibalism, what its supermassive central black hole actually is, why the galaxy has stopped forming stars, what the surrounding cluster looks like, how vast IC 1101's spatial extent really is, what its long-term fate looks like, the catalogue ancestors that gradually revealed it, and where to find its constellation in the sky. The picture, when assembled, is of a single very large object that has been quietly building itself on its own clock since the first few billion years after the Big Bang. It is still there tonight. It is still slowly growing tonight. It will be there, slowly fading, for the rest of cosmic history. Here is the broader context for the science. Understanding IC 1101 is not just about understanding one galaxy. It is about understanding the general process by which the largest gravitationally bound structures in the universe assemble themselves. The same physical processes that built IC 1101, dynamical friction, hierarchical merging, virial shock heating, AGN feedback, gradual quenching of star formation, built every other supergiant elliptical, every other CD galaxy, every other central cluster galaxy. IC 1101 is, in this sense, a particularly clean and well-studied example of a much more general process. The work that has gone into measuring it is, in effect, a calibration of our understanding of how galactic structure formation operates at the largest mass scales. Every other galaxy cluster benefits from what we have learned about Abell 2029. Here is the very deep cosmic context. The universe contains many galaxy clusters. There are perhaps 250,000 galaxy clusters above a certain mass threshold within the observable universe, depending on how exactly the mass threshold is defined. Each cluster has a central galaxy. Each central galaxy, in most cases, is a CD galaxy, or a closely related supergiant elliptical. The universe, in this sense, contains hundreds of thousands of cathedrals like IC 1101. We have, in detail, studied perhaps a few hundred of them. The remaining hundreds of thousands are observed only in surveys, characterized only by their bulk properties but not studied in detailed, individual ways. The cathedral that we are looking at tonight, IC 1101, is the one that humanity has chosen, perhaps somewhat arbitrarily, to study most carefully. There are many others. They share, broadly, the same physics. They differ in detail. The general picture, refined in IC 1101, applies to all of them. The constellation Serpens is in the spring sky in the northern hemisphere. On a clear evening, when conditions are right, you can look toward the head of the serpent and know that 1 billion light-years beyond the foreground stars of the constellation sits the cathedral. 100 trillion stars. A diffuse halo extending 6 million light-years across. A supermassive black hole at the center. The central object of a cluster of 2,000 smaller galaxies. The largest single galaxy that human astronomy has so far measured, slowly growing, slowly fading, on its own 10 billion year clock. You can let it go, for tonight. Here is the further small thing about the deep observability of these systems. The kind of work that is done on cluster central galaxies like IC 1101 is, in many cases, the kind of work that pushes the limits of what current instruments can do. Mapping the faint outer halo of IC 1101 requires exposures of many hours on large ground-based telescopes, with careful subtraction of the sky background, careful flat fielding to remove instrumental artifacts, and careful modelling of the point spread function of the optics. Each of these steps is its own technical challenge. The astronomers who do this work are not glamorous figures in the popular imagination, but they're patient. Careful work is what produces the surface brightness profiles that tell us how IC 1101 is structured at the very edge. The cathedral has been measured in the very faintest reaches of its outer light by careful, technical effort. The edge of the cathedral is genuinely visible only when you know how to look. The instruments are sensitive enough. The atmospheric conditions are good enough on the right nights. The post-processing pipelines have matured enough. All of these conditions together make the very faintest measurements possible. Here is what continues regardless of whether anybody is paying attention. The work of observing IC 1101 continues. The Chandra X-ray Observatory continues to map the hot gas in the surrounding cluster. The Hubble Space Telescope and JWST continue to refine the measurements of the galaxy's stellar populations. Modern cosmological simulations continue to test their predictions against the observed properties of the galaxy. Each year, the picture sharpens slightly. Each decade, new instruments add new data. The cathedral remains, in its slow gravitational equilibrium, one of the most carefully studied objects in the local universe. Good night. Sleep well. The Cathedral of Stars is still in its slow assembly. The light is still arriving. The mass is still what it has always been. Here is the final, small thing to hold before sleep. The galaxy has been there, slowly assembling itself since the very first epochs of cosmic structure formation. It was there before our solar system formed. It was there before the Earth had cooled. It was there before life on Earth had evolved into anything more complex than single cells. It will still be there tomorrow morning when you wake up. It will still be there next year and next decade and at the end of the century. It will still be there in 10,000 years, in 100,000. The cathedral on its 10 billion year clock simply does not respond to any human-scale timeline. Whatever is happening tonight in your room or in your life, the galaxy keeps its own time, on its own scale, far away in the head of the serpent. There is something quietly steadying about that. The universe contains structures so vast and so slow that they make every human concern look small in comparison. They are not indifferent. They are simply on a different clock. The clock has been ticking for 13 billion years and will tick for many more. Sleep well. Here is one further small observation before the quiet close. The number of stars in IC 1101 is comparable to the number of grains of sand on every beach on Earth. By rough estimates, there are about 7.5 times 10 to the 18 grains of sand on Earth's beaches. The number of stars in IC 1101 is about 10 to the 14, or 100 trillion. So IC 1101 contains, by stellar count, roughly one star for every 10,000 grains of beach sand on our entire planet. Each of those stars is itself, in many cases, a sun like our own, capable of hosting planetary systems and the kinds of physical processes that, on at least one planet around at least one star, eventually produced beings capable of measuring how many stars are in the galaxy. The arithmetic of comparison is, in some moods, almost devotional. The universe contains, in this single object, an enormous number of separate possibilities, each of which has had 10 or 12 billion years to play itself out. The cathedral has been quietly running its experiments for the entire history of life on Earth and longer. The galaxy is older than we are. The universe is older than the galaxy. Both are still here. The light from IC 1101 reaching telescopes around the world tonight is, in its own quiet way, the deepest record we have of how cosmic structures grow. It has been arriving every clear evening since the invention of the telescope. It is arriving now. It will keep arriving for as long as the galaxy burns and the Earth turns. Sleep well. The cathedral has not yet finished its long, slow assembly. The light keeps coming.